Earlier this year, I attended the ShmooCon cybersecurity conference, and after solving a binary exploitation capture the flag challenge, I won this mug. It's a pretty cool looking mug. It's from RET2 Systems. It's a very nice Yeti and actually has a pretty cool little, hey, open up whenever you need a sip. And it actually complements the original water bottle that I've had from RET2 Systems back since 2020. You might have seen this in the background of a whole lot of my videos. Super duper nice, super duper cool, and it's been my water bottle ever since for those past 2 years. But anyway, in this video, I want to show you how I solved that binary exploitation challenge and how I got this cool mug. So hey, in full transparency, this is a sponsored video, but I do want to shine the spotlight on RET2 Systems. If you haven't heard of them, they are a super cool company that focuses on a whole lot of cybersecurity and security research in the realm of reverse engineering and binary exploitation. That is finding vulnerabilities and exploiting them, finding these crazy 0 days, and just doing really cool like Uber Ninja Elite stuff, deep down in the disassembler, deep into the debugger, and phenomenal low-level work. They not only offer their research services, but they also offer training. And they have a super cool online platform for WarGames in learning some of that low-level work, reverse engineering, and binary exploitation. And I want to show you this platform because it is honestly really, really cool. If you're interested in getting your hands on it, they do have an online demo where you can kind of poke around and play with it. And of course, an option where you can go actually check out the product and purchase and do whatever you need to do. If you're interested, they also have a course and showcasing a lot of these security research fundamentals and getting into these low-level vulnerabilities and exploits. But I would like to hone in on the challenge for the ShmooCon 2022 Yeti Mug Challenge. So I'm going to log into the platform, fire up this challenge, and get started. Alrighty, I am here in the online wargame platform for RET2 Systems and the ShmooCon Challenge. It looks like this is the Hacker WORDLE Challenge, and it says the RET2 Systems Corporation rewrote the wildly popular game WORDLE in its favorite language, C. Now the game is blazingly fast, but is it secure? To solve this challenge, you must pop a shell and exfiltrate the flag. This challenge is time sensitive. Okay, and this was all for while I was at ShmooCon in person. But it looks like that is some of the pretty cool instructions on this pane over on the far left. In the middle, I can see I have the source code for an application in C here. Looks like I could also tab in between data, which looks like just either bytes or yeah, the hex representation of the data of the object. Yeah, you can see the RO data and other binary sections here. Here's the GOT, global offset table, PLT, procedural linkage table, data, BSS, etc., etc. Also have disassembly. If we wanted to look through raw opcodes or Intel assembly instructions here. It says, hey, this is the disassembler view, which we have provisioned for you. It might be missing a few bells and whistles, but it can help us crack more systems than we can count. If you want to press space, that'll toggle the disassembler between graph and linear view. That's pretty slick. We're pretty sure this code is quite sketchy. Can you make any sense of it? So I'm going to move this debugger over here on one side and try to see, can I actually take a look at the control flow graph? That is super cool. Can I zoom out? I can. Oh, that is so cool. Okay, so here's the main function, showcasing all that it does here, branching off to different if statements and things that are done. I like that. I got to admit, I am a fan of the source code, though. Rather than having to dig through all these instructions, maybe it's worthwhile kicking a look through the source. We also have the debugger over on the far side. I want to... What is this? Looks like WarGames GDB, so WDB is the prompt. What do we have available for us? Some new notifications. Great, you found the debugger terminal. If you've used GDB or the GNU debugger before, then you are in luck. This one is virtually identical. Here's a few useful commands you can run as usual to run the binary. Set a breakpoint with an address using the asterisk and the memory address. Info on the registers to dump the assembly registers. Dump 16 bytes of memory at a specific register, prefix with a $sign like RSA. Step I to step a single instruction, continue to resume execution. And you could actually check out more with the help command, which we just did. Pretty slick. And we can drag that over whenever we want to. Or make it go away. I guess if you click on that, it just flies. But yeah, that's pretty slick. Also have Python. So we have both the interpreter and like a scripting space we could look in. We could also toggle between Python versions if you like Python 2 versus Python 3. Got an achievement. Also, we should be using Python 3 because that is the right way to do it. But I'm assuming I can run this. Ooh, yeah. Okay, and that'll fire up the game. So if it'll just run the exploit script, which right now looks like it has Pwn tools-like functionality where we have a P64 and U64 function just defined to go ahead and pack or unpack data representations, and we interact with the process. And you could call read until or send line or other functions to be able to interact with this. That's super duper slick, but we can also just play and work with Hacker WORDLE here. So before we dive into the source code, let's go ahead and take a look at what Hacker WORDLE is or what we should be doing. I'm assuming this operates just like the regular game WORDLE, right? So I could try and guess a word. I'll guess hacks. Ooh, okay. So HA is all not in the word that we're trying to guess. The letter C is, but it's not in that position. The yellow indicates that, okay, that C letter is in the word, but not in the position that you had it enter. So could I use cakes, I guess? Ooh. Okay, so C is in that position. Cakes. E is in that position, but A, K is still not going to be present, and S is not. So what other words have C and E in there? Creed. Ooh. That E doesn't help me much because I don't know if I duplicated the E, but now I know there's an R in there, I suppose. What else are word? Cared. No, that R is not in the right place. I wanted to move it, but it didn't work. Oh, is it like cyber? Oh my gosh. Okay, so it's cyber. Cyber is the word. That's so leet, right? Because it's the Hacker WORDLE. And then it solves the application and then closes and exits the process. Press enter to return, and then we're back into interpreter. Okay, so we could play with our debugger. Yeah. And I can hit Control L. Oh, what is this down here? Are these like checkpoints? Yeah, solve the WORDLE at a special point. I didn't get that. Solve the WORDLE at a special point. Is it like right at the start? Order of operations? Ensure you can play more than just 6 rounds. Corrupt the return address of main. Okay, so this is for the actual exploitation portion, right? I can't just solve the challenge like I did and expect to get a flag. I think the instructions were to pop a shell. Yep, okay. Pop a shell and get a flag. So if I run the program, I'm in the debugger here, so I can just hit run or R as a shorthand for it. Now that we know the word is cyber, okay, it's not on the very, very first iteration that is a special point. Let's go through the source code. We literally have the source code in front of us. So we're in C, and we have some preprocessor definitions to include wordle.h, which is hidden for simplicity. So that might include some other functions or niceties that we just aren't being presented with here. But we have some other constants defined where the word length is 5. That makes sense. We've been seeing that in the display here. The word guesses, or the number of times that we can guess, is 6, right? As we can see, hey, 6 guesses remain, and however many times it took us to guess. We have a struct defined for the game itself. We have the number of attempts that we've made that it's keeping track of. And then the matrix, or that grid, set up as like a 2-dimensional array, right? So words, 6 rows, word guesses, and then the word length is 5. So a 6x5 grid? Yeah. And then, okay, just representations of whether or not that is solved or game over. I'm expecting those to be Booleans. I don't know why they are char or care, but okay, whatever. That's set up. And then we have our main function. We have init wargame called, which I'm going to assume is something probably stuffed in wordle.h. I don't think we'll be able to track that one down. But we go ahead and create an object representation or like something to store our game structure, and that is state, yeah. And then the buffer. A buffer is defined with 16 characters. Probably going to assume that's like a string input that we'll go ahead and read in, right? Hence the name buffer. And then we do a while loop. So this must be the main loop of the game, just as we saw. Hey, we enter a word if it's right or wrong, blah, blah, blah. And just keep moving through. So while not, that's that exclamation point, state game over, or those are the two vertical pipes there, state.solved. So while you have not completed the game, whether it's over or you finished it or not, it'll print the game based off of our state object, right? So that is, again, probably print game is a function inside of wordle.h. We can't see it, but it's probably pretty simple. Hey, spit out the grid, right? Now, it asks us, hey, enter a word. Yeah, okay, prompt the user to guess a word and exit if it is the end of file. Oh, like if I just hit R and then hit enter, oh, and it just tells me invalid input. Like, if I entered sub for subscribe, yeah, no, okay. So we need to have the proper length of 5 letters given there. Anyway, we enter a word and then we retrieve it with fgets, retrieving into our buffer, given the size of the buffer. Okay, so about 16 characters we will read in. Can I enter, like, here's a bunch of A's. Still doesn't like it. Oh, and they checked for that down below right here. So they're reading in standard input, just regular standard input, and it just craps out if it's not happening. But we will go ahead and actually, if we were read in that buffer, we'll go ahead and index it at strc span. Is that a fine way to say that? What is that? C function? Google, what are you telling me? strcspan. The C library function strcspan calculates the length of the number of characters before the first occurrence of characters present in both the string. Oh, so it's like looking for a substring? Calculate the length of numbers of characters before the first. So it's like finding the index of a string. It has to be made. So we take our buffer, the full thing that we entered, and we're looking for the index of new line, or when we hit enter, yeah? Okay, so we're just setting that, the index at that position, to 0. That must be like forcing the null byte to terminate that string, right? So that's when I enter like a word, hello. Yeah. I hit enter to send that hello line, but it's now replacing that new line character with 0. So we can just do proper C stuff. Low-level language shenanigans and dark voodoo magic. We check to verify, okay, now is the strlen, or the length of that string, given the buffer, if it's not equal to the word length, then it tells us, look, hey, dude, you had the invalid input, which we saw previously when I tried to enter, like, please subscribe or whatever. And then it will continue. So it'll move through the next iteration of our loop. Okay. So the game will end if the entered word matches the encrypted WORDLE. Ooh, and the WORDLE is encrypted. Which is probably why we weren't able to know, the answer was cyber until we figured it out, right? So compare encrypted is a function that we are seeing used. See if that's down below or something that we could actually review. But we check against our buffer with the WORDLE, given the word length. And if it is returning true, then we just set the state solved equal to 1. So that's telling the software, telling the program, hey, we solved it. We entered the correct word. And the game will end if this is the allowed last guess. So else if state attempts plus 1 is equal to word guesses, and the state game over is equal to 1. Is there something weird there? State attempts plus 1 equals word guesses? Game over is a way down here. No. I don't think that's weird. I don't know yet. Anyway, we'll keep cruising. We'll see what we think. I've got all this stuff at the top here. Sorry, I figured that's distracting. Once that logic is all done, determining whether or not we've solved or completed the game, we copy the word onto the WORDLE board and encrypt it. So strcopy. Not using strncopy. Could that be suspicious? Could that be weird? Like that on its own is normally a dangerous function, right? Because there's potential for a buffer overflow there, which might be our venue. But our buffer is forced to be word length, or just 5 characters, so that's not all that helpful. And it slaps it into state words, state attempts. And state attempts could theoretically keep increasing, right? Hence, yeah. So it does. It increments the number of attempts as you keep going through this. And we encrypt word following these based off of the word length. So what, and then we just print the game again? Yeah, okay, cheesy. Our encryption helpers are other functions that we have here. An encrypt word, that function that we saw being called, just takes a string or character array based off of a length and encrypts it with an encryption byte. Ooh, and that encryption byte looks like a constant, but we don't see that defined anywhere. That's probably tucked in windows.h, or excuse me, wordle.h. So maybe we could try to track that down. But it just loops through every single character and then XORs it with the encryption byte. So all this is a simple XOR operation, right? Then we compare encrypted, another function that will take a user word versus our secret word, which is the actual Wordle solution, right? As we know is cyber. And based off the length, it goes ahead and encrypts these, just as it did previously. It does this with uppercase and lowercase. Oh, so it does it. You can see the comments here. This is just a case-insensitive compare. The two words passed a case-insensitive encrypted compare, telling us, hey, whether or not we had the correct word. We know we found the correct word, which was cyber, and that is okay. I don't think there's anything wrong or like insecure or vulnerable with this process, right? It's literally just XOR, which we already know the solution. It's not like we're trying to find, oh, what is the secret cipher message here? We know that it is cyber, and we could probably track down what the encryption byte is. And compare encrypted isn't anything that we need to like take advantage of. There's no vulnerability in us doing this comparison of XOR. And way down here, we have a RET2 system function. This is probably just our win function, right? If, we were able to jump to this, return to a system call where we can just call binsh. This is just our win function built into the program. So we're able to jump to that. Okay. So that was a finally a review of the source code. Now, let's figure out our encryption byte. We know that is in wordle.h, so I'm assuming like we could get into our disassembler. Can I break out of this? Yeah. And if this is just like GDB, I could just straight up disassemble functions, right? And I'm assuming we still have debug symbols or whatever, so I could just disassemble encrypt word. Yeah, okay, cool. So this shows us at least the instructions and how this function goes away and happens. You can see we have a push RBP to push 64-bit base pointer onto the stack, move RBP to RSP. So we're adjusting the stack pointer based off of the base pointer. Usual 64-bit function prologue, right? Blah, blah, blah. I'm kind of going to ignore all of this crap because we know how this function works. We literally have the C source code. All I care about is this XOR operation. So the register that it was XORing was ECX, collector register, counter register, you could, whatever name you want there, with hex 29. Okay, so that is good to know. Our encryption byte is hex 29. Great. Now that we've figured that out, how do we actually exploit this? Like, the STR copy doesn't work all that much because, again, this is limited to 5 characters. There isn't a gets in here that's another dangerous function. What is the gimmick? Do you guys see it? Do any of you guys already know? Like, what the heck? Just play the game. Cyber works. Okay. What if I just like bump around? CCCC. Just play with the thing. Yeah, obviously those are all good. I can't add anything more, right? If I add another extra character, it's an invalid input. So why? Correct letters. B, 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 B. Correct letters. This isn't all that interesting. E, 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 E. At least I got a pretty picture. Cyber in a nice diagonal. Whatever direction that is with the camera. And then cyber is our final one. Hello? What the heck? What the heck? 0 guesses remain, but it's still letting me guess. What? Hello? Whoa, whoa. Okay. Execution solved. Solve the Wordle at a special point. And it got 7 out of 6 guesses. Why did that happen? We correctly solved it then, and we got this checkpoint, but what is so special about that? All right, let's look at the source code, because is that like the condition that's wrong? While not state game over or state solved. So once we've solved it, even if this is true, game over is apparently still false since it kept letting us guess just then. Like it told me 0 guesses remain and it still asked me to enter a word. So true and false, this is going to give me an or. So true or false becomes true because one of the true statements is in there. And then a not negates that and makes it false. So we should have stopped looping, but we didn't. What is going on? The game will end if the entered word matches the encrypted Wordle, which it did. We solved it with cyber. So state solved equals 1, which up in our game, that's over here. The game will end if this is the last allowed guess. State attempts plus 1 equals word guesses. State game over equals 1. Yeah. And that gave us the 7. But why do we keep going? STR copy, state words, state attempts buffer. Oh. Wait a second. Look at how this structure is defined. It's doing this in a bad order. Like it's checking for the validation, I think the wrong way, right? Like, because up here, if you could see, we can see that we set the very, very last word's new line character to a 0. Based off of the buffer value. And then we end up clobbering state word, state attempts buffer with its value. Does that sort of make sense? I'm sorry. Let me walk through this, noting the way that this is defined. So we have our grid, our matrix, word guesses, 6 rows, 5 columns based off word length. So say we're at the very, very last row, and we fill in all of the letters for that word length. We've entered the full word cyber, 5 letters, C-Y-B-E-R, and then we add a null byte for our new line character. So that changes it to be 0, right? Based off of this function or this instruction right here. Buffer, strc span, new line equals 0. So our new line being removed as 0 is actually breaking out, I think, of this matrix. Does that make sense? Because word length is 5. We read in 16 bytes, but then the 6th byte, which is our new line character, has just become 0. So that would break out of this character matrix when we just use str copy, because there is no bounds checking. It's not using strn copy. So even though we set if compare cryptid buffer Wordle word length equals blah, 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 state solved equals 1, state solved is going to take this like space over here while our word length is just beside it. But we pushed just a little bit outward and are clobbering the solve value. Once we set it to 1, our str copy function, we've now changed that back to a 0 because the very, very last character has been Our new line character was transformed to 0. So it's as if we've never actually solved it, if and only if we solve it in the last row. Okay. Kind of wild. So that makes sense and has we solve the Wordle at a special point. But now how do I ensure that I can play more than just 6 rounds? My attempts needs to be clobbered some way, somehow. Can I just add a null byte as another? Because fgets doesn't care about null bytes, right? I don't think it does. I think fgets will just read null bytes. Does fgets read null bytes? What do you got for me? Yeah. Okay, fgets, yes. Fgets is specified to behave as if the repeated fget C in storage for blah, blah, blah. No special provision is made for the null character. I dig it. So that, I think, could work. We could clobber attempts, which will follow right after our solved or game over portion, right? We'll clobber it every single time if we just had a null byte after it. Let's try and script that. Yeah? Because we have our interactive, we want to get data and read until new line. So let's just try and send hello. Perfect. That fills it in with hello. Now, can I send a \x00 and still run that? Yep. Okay, so that it has no issue. So let me do that 5 times for underscore in range of 5. We send all this crap, and let's use the proper word there. Oh, wait, no. We have to send garbage the first 4 times. Or 6 times. Yeah, 6 times. So 6 times to solve it, right? Because we have 6 guesses. So we have to send it garbage 5 times. Hello, hello, hello. And then we'll solve it properly. With a null byte at the very, very end, because that is how we could modify the game over value. Correct? I think so. Maybe we might need more null bytes, but let's try it. I'm going to run this. Blah, blah, blah. Cyber, 0 guesses remain. And let's try and send it one more time. What should we say? Hacks. Let me run that again and again and again. Oh, and now you think that I solved it. But should I have had another one there? x00? Where's attempts? Attempts is above, so I can't clobber that. We can't, like, based off of how the variables are assigned, we can't modify the number of attempts. We can try and clobber the state of the game over variable, right? Let's add a couple more zeros, or like null bytes there. Blah, blah, blah. And then I theoretically had another thing. Can I just keep sending hacks? No. Why not? Wait. Our new lines are now ruined. Because I'm not sending a new line. I'm adding the... I think? Can I literally send a new line like that? And send a new line? This is confusing. So let's take this back down a notch. Don't send as many hacks after we send the actual solution of cyber. And then our null bytes could follow. Let's start with 1 again to see. Because I'm saying, yes, the null byte clobbers solved becomes 0. And then the null byte that follows could set our game over to equal 0 rather than 1. Yeah? Please? Blah, blah, blah. 7 out of 6. And then a process terminated. But what if I send it more? No. Am I not understanding that? What if I sent it null bytes just like that? And let's give it a couple more, I guess. Can I wrap around in any weird way? I can still guess, but I didn't send another one. So let's send my hacks with more null bytes following that. Blah, blah, blah. And that still doesn't let me go further. Lame. What if I send cyber again? I can't get past 7 guesses. And I need to. Can I send just a crap ton of null bytes? About 5 null bytes. What the what? That's still letting me send stuff. Go, go, go. That gives me more guesses. 0 guesses remain, 0 guesses remain, 0 guesses remain. Am I sending actual things though? Like that sketches me out. Hello? No. Even though I have tried more things, it's not really letting that happen. Okay, so I'm missing something, and I got to figure something else out. Give me a little bit of time to think on this one. I don't know if this is the right thought, but the if statement to set solved happens when it's the correct one, and then this game over thing only happens in an else statement. But I feel like I have to keep sending cyber, cyber, cyber. Do I not? Let's send cybers. 7 out of 6, but then it's still solved. Let's send a bunch more cybers. No. So this one has to be correct, and the other one needs to be wrong. But this is exactly what we were testing before. That didn't work. Ensure you can play more than just 6 rounds. All right, keep thinking. Hang on, do we even have to solve it at that right time? Can I just send 6 hellos and still get prompt for guesses? Try and do that. No, I fail. Okay, so it does need to have that solved. Get cyber back there. Yep. Now, how do I break the attempts? Can I make it a second new line? That would seem weird. I don't know why that would do it. Or if they trying everything. Nope, still solved. Why? Can I send it multiple things in one line? Let's do a hello. So my null byte will be there. And then another null byte. Well, hello. Because fgets will keep reading, right? I'm just going back to what I did before. This still doesn't seem right. Still not right. Because solve is going to get through it. How do I get that? Wait, are my null bytes encrypted with the XOR? That's probably dumb. Can I get back to real Python for a second? Yeah. Like, what is hex 0 XORed with hex 29? What is that in hex? Hex 29. So, but that doesn't happen until after the encrypt word. So maybe that's not all that useful. What happens if I XOR hex 29 with hex 29? It's just 0, right? So hex 29 could potentially be my null byte? That seems dumb. But is that worth a try? What the heck? Oh, now I don't have my actual null byte in there. So that is still needed, right? Or a new line. Maybe the solve has to happen. But then the other hacks can have the null bytes that are XOR'd? I don't understand. It's giving me other guesses. Theoretically. Right? Tests. No. Okay, I got it. I got something weird. I tried to send it the encrypted hex 29s, which were null bytes when they're encrypted, right? But why does that work? It gave me a -1 guesses remain. Can I... And that gave me the achievement, hey, you can play more than 6 rounds now, but like... How many more can I play? -1, -2. Okay, so now I'm decreasing all these things. Cool. And I can just keep sending this now, can't I? I guess. Will I ever get to a point where I clobber something? Blah, blah, blah. Does that work? So let's loop this. And let's just see how much we can break, because now we need to corrupt the return address of main, right? Now, what am I overwriting, though? I'm clobbering the attempts in some way. Is that how's that happening? Wait a second. Once we run cyber, and we don't even need to have that null byte there, that brings us through to the... Hello? Oh, I started to write a for loop and I didn't finish it. That brings us through to the 6th attempt. But then once we go through our 7th iteration, attempts is at 6. So when we str copy state words at index 6 being our buffer, we now set this, or the position beyond this, which would be solved and game over, and clobbered by 5 to the hex 29, and then we encrypt it, which puts it at a null byte. So that section afterwards is now being brought back to 0. So that, I think, works. I think. And we are now leaking and pushing past our struct, are we not? So let's try to do that for loop. Let's just do a for whatever range. Let's do 5 again and just see how far we go. I have no clue if this will work. Oh, please. In. I forgot the keyword. Blah, blah, blah. Ooh. We corrupted the return address of main some way, somehow. Am I dumb? All right, I need to figure this out. So I tried to get all these things wrong. Ooh. I think I just needed to tell it, like, hey, I want to leave. I want to stop. So, like, send it all the weird crap and then try to solve. So, like, after we've sent all that shenanigans, go ahead and just break by solving it. Tell yourself to return out of the function, right? How about that? Oh, unexpected indent. Yeah, you're dumb. I just want to make it clean on the screen. Funnel through it. Now break. Now, RIP has a segmentation fault, so we're clobbering it some way somehow, but I don't know how yet. Well, we filled it with null bytes earlier, did we not? Yeah, like when I had that earlier, I filled it with like, let's try and amp up the number. Let's bring it to 7 and see what breaks what where. Now RIP is just all null bytes. Okay, so something's whack somewhere, but because this is being encrypted, it's now turning it back into null bytes. So I need to figure out where these things go and how. So let's send 5 A's. Well, let's figure out where the threshold is when we start to see null bytes. How about that? Let's try that at 6. Good. RIP has all of these. 1, 2, 3. Oh, God. 4, 5, 6. I can't even read those. Is that 5? 1, 2. There are too many. It's too confusing. I'm just going to switch this to 5 A's. And see how that encrypts. We need to be able to get what the return address that we want translated would be. But, that still gives me nothing. That didn't work. What? That didn't get a seg fault that time. Because we didn't even send it the XORs. It just solved. Oh. So we need to at least send one that is our weird broken stuff. Yeah? Hex 29, hex 29, etc. Okay, now go. Now see if you kill it. Yep, negative guesses. We're meffing stuff up. And then 6868686868. So A is all along. Weird. Where is the threshold? Where do I not have A's? So 68 is what we're looking for, right? Blah, 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 blah. Looking at RIP. Here is 2, 3, 4, 5. How do we get a 6? Oh, we got a 6 in there from a previous iteration, right? So it's probably just filling weird parts of RIP some way, somehow, somewhere along. We just need to find where that gimmick is happening. Okay, did I change that to the same value or did I move it forward? I don't even... What did I just do? So let's toggle that again and see if we get any difference here. Yeah, now RIP has 168 and then other stuff. So if I were to set this to 3, do we have any 6/8s whatsoever? Any of our A encrypted renditions? No. Okay, so that is necessary. We need to get weird padding, and then let's send line 1A and then BBBB without an iteration. So 3 iterations will get us to some portion, and let's see if our A's get in there some way, somehow. And which of them is in the way. If that makes remotely any sense. Now I don't know which is which. my 6B at the end here could be anything. Or depending on how that's encrypted. I don't quite know. I gotta be honest. I don't know where or how it's getting those values. Oh, actually, our A's are in RBP, and in 64-bit, you do a weird different thing. The B's are getting in there. They're not clobbering our IP, though, yet. The 64-bit does the weird thing where the base pointer is actually important before however you get into clobbering the instruction pointer, right? I think I showcased that in a recent video, I think with Matt. We talk about it a little bit. I don't know. We'll figure this out. Let's send A's, B's, and all of these without looping. A, B. Now let's send C's. Whoa. And let's try some. That's 6 characters. Nope, wouldn't like that. And then D. So that's 4 iterations. And we might be clobbering RIP some way, somehow. Okay? So 6C, 6B. We aren't fully there yet. Let's try more. Okay, RIP is looking good. Oh, God. The question is which of whatever offsets is what? This is not fully useful yet. But we are making a difference. We are changing the instruction pointer in some way. So this isn't awful. We can figure something out. RIP. 6F, 6F, 6C, 6D. Oh, no. The question is now what is where? We are properly clobbering RIP, but we don't know what corresponds to what. Let's get back into Python and let's see what's encrypted with what. Oh, God. What did you just do? Am I in Python? No? I don't want to see the disassembly. Enter to return. Okay. So RIP has 6F, 6F. 0x, 6F, XORed with 0x29, our encryption byte. We know that that is 70. What is the hex value of that? Hex 46. What is the ordinal value of that to get represented as a character? Is that how that works? No? What? CHR. What is the character represent? That is F. So 6F is our F. 6F. Question is which? Because we have 2 6Fs. I'm going to assume, like, if this were like normal, okay, 8-byte longs, as you would expect in 64-bit, we could probably figure this out a little bit more, a little bit better. But because we have to work in these 5-byte chunks, because of how the Wordle game has to be played, the only successful 5-byte one that we see is 6C, 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 6C. So what is 6C? That is our E. So we could change that to be something important in an order that we might care about. Let's do 1, 2, 3, 4, 5. And then we could determine what direction this needs to be read in, or whether it's backwards or front or whatever the heck. Yeah. Okay, so 1C, 1D, 1A, 1B. My God. And then a 1-8 randomly? What? Oh, that's not helpful. Where's the 1-8 coming from? Whatever. What is the value that we need? What is our RET2 system function address? We're in our debugger. Can I just disassemble RET2 system? So we need hex 0, so we need 400D D2, right? That is the address of the function call that we need. So that needs to be XORed in some way and somehow. We could probably U64 shenanigans that. or figure out what that needs to be in actual endianness. I think it just needs enough padding. D2, 0D, 40. That's 3 bytes. Yeah? So 1, 2, which is 1, 2, 3, 4. I don't even know. Is that right? Is that wrong? Is that... What am I doing? What is... Here. Pack that into 8-byte representation. Let's just do that in Python. Take me back to actual Python, please. Stop. Press enter to return. Import struct. Give me that. What is P64 of our good friend, the function of RET2 system? Ah, yeah. Okay. So what is U64 that? Oh, yeah. Give me that. Ah. Yeah, I know. Perfect. Perfectly not helpful. So anyway, we have 5 extra bytes there. So that's just fine. Question is, which go where? Well, let's start to play a little bit of whack-a-mole, right? Let's do it. I don't mind. I don't mind if you guys don't mind. So this is the hex-encoded rendition of our win function. Win function can equal that crap. Yeah? We knew from earlier that 6F, 6F needs to be 0, 0. In which case, those are just all of our Fs. So because those are the first two, that can be 0, 0. That can be null bytes all the way along, right? Let's see if that goes for us. Spin it up. Why is your win function? Oh, my quotes are dead. Kick it off. Boom. RIP does not work. What happened? What happened to my Fs? We were just there. Did they encrypt it in some weird way? Wait, no, they need to be encrypted. That's the problem. Hex, all these things need to be... Shoot. These all need to be encrypted in their XOR renditions because that's how they get passed. So this needs to be hex 29 all the way along. That will give us 0 zeros, correct? Yeah. Okay. So now 6D. What was 6D? CHR of 660 XOR with 29. That is our D character. So one of those needs to be D2. In which case, what is hex D2 XORed with hex 29? That's 251. So we need to get the hex value of that. Hex FB. So this can be FB all the way along because there's only one character there that matters. Yeah? So now RIP should have all the zeros in the front, and we should have D2. No, something horrible happened. It's because I only supplied 4 of those values, not 5. That's okay. I was wrong. We can move forward. Yes! D2. Perfect. Now we need to arbitrarily guess where the crap things are for these others. Let's try stuff. Hex 29 for null bytes. Hex 30, hex 31, hex 32, hex 33. Oh god. So we should hopefully be able to see some difference in that, how that XOR gives us these values now in the middle of that. Yeah, okay, cool. So this is our null byte, which needs to be 0, which need to map to the position of 0D. And where are the others at? Weirdly increasing. What is... Let me out. 0x19 XORed with 0x29. That is 48, which in hex is 30. So 30 is the other position. Okay, so we just need 0D. Hex 24 needs to be that null byte character. And then hex 30 should be 40. Correct? XORed with it. My goodness, I'm moving things. I'm sorry, this video fell off, everybody. Hex 40. Hex 69. And then all the other positions need to be null bytes, which means that all the others need to be 29 because they're XOR encoded or XOR encrypted. So that should set RIP to the full win function value that we need, which is the address of RET2 system, which will call and execute system. Let's do it. There's our prompt. That's it. Yeah! All right. Debug flag captured. Run live mode for the real flag. All right. So this is a horrible, god-awful script, but we kind of played a little bit of whack-a-mole and we figured it out and we did it. Let's toggle this thing into live mode. And let's fire it off. Done. Who am I? I'm still root. We have the flag in our current directory. Flag WORDLE lead. Oh. That was awesome. That was fun. That was a really great time. All right, so we did it. A little bit of whack-a-mole, a little bit of live learning, but that troubleshooting and debugging and figuring out the rabbit holes that we just fell into, that is how, hey, I ended up scoring this mug over at ShmooCon with the RET2 Systems booth, and it was a ton of fun. Thanks so much for sticking with this video. I had a lot of fun with this, and I love what RET2 Systems is up to. For one thing, all their super incredible research and offering this platform and these war games and these challenges and activities that can help you grow in reverse engineering and binary exploitation, having that environment literally all within your browser, like having the debugger, having the Python script, having the disassembly and everything. That it's just cool. It's just nice, and I hope you go play with it. You can check them out online at ret2.io, and I think you can find them at wargames.ret2.system. Systems? Yeah, wargames.ret2.system. Sorry, guys. Thank you to RET2 Systems for sponsoring this video and all your support and all the crazy, nerdy, silly stuff that we do here on this YouTube channel. Thanks so much. I love you guys. I'll see you in the next video. Take care.